Practice Problems, Module 2. We have already gone over in principle the ones that you stated were the most difficult to you, so let's just go ahead from the beginning. I don't think it would be a waste of our time to go through these again. I'm just going to start from the front and go through. Again, we've already covered in concept the most difficult ones for you. And what I'm going to do is just, maybe we'll read the problems, and again, what I think one of the most difficult things for students is to see the word problems and write it down as a chemical equation or as a mathematical equation with some particular chemical symbols into it that are placed into it for chemistry. Module 2, practice problem number 1. It says a chemist uses an experiment similar to experiment 2.2. Now, for some of you that meant you had to go back and read experiment 2.2. It was in the reading and was part of the required reading, but maybe go back and re-look at the material. Similar to 2.2, but what did they do? Well, they decompose. Now, I gave credit for the word decomposition, like whenever you take a molecule and break it into its parts. Please understand, when I use the phrase decomposition, that is a chemical reaction, okay? These things aren't decomposing. Decomposition is a type of reaction. And I give credit for decomposition when the textbook says, or in the answer key says reaction. But I want you to understand that decomposition is a particular type of reaction. We're going to go through 4 specific types, four general types actually, of reactions later on in this course. And one of those types of reactions is a decomposition reaction. Okay? So when you say, in this place here, when they say decomposition, that's telling me that it's one of the 4 particular types that we're going to be looking at. So it uses an experiment similar to 2.2 to decompose 150 grams of water. We're going to decompose, so we have a reaction arrow. We're starting with something and we're going to end with something. And this is a decomposition. We're going to decompose what? 150 grams of H2O. Just like in math, setting up the problem is the most important part of getting the right answer. Set it up right and then do legitimate processes, legitimate steps from A, B, C, D, and all the way through. 150 grams of H2O becomes, through decomposition, okay, he finds that he makes 16.7 grams of hydrogen. Now, again, don't worry that I wrote H2. You may have written hydrogen. I don't expect you to know that it's a 2 right now, even if you put an H in here. That's fine. You're telling me it's hydrogen. Later on, H won't be acceptable. It'll have to be H2. But for now, hydrogen, however you wrote it. 16.7 grams of hydrogen from the decomposition. How much oxygen must he have produced? So you look at the original molecule, you've got hydrogens and oxygens, and it's going to produce hydrogens in decomposition and some amount of oxygen, right? My H2O becomes H's and O's. I started with 150 grams, and I end with 16.7 grams and some unknown amount of grams. Conservation of mass tells us that the mass of the reactants equals the mass of the products. However much stuff I start with, I have to finish with that much stuff. And by stuff, I mean matter. And matter is measured in grams. I have to start with and end with the same amount of stuff. And if I start with 150 grams, that means I have to end with 150 grams, correct? I start with 150, I have to end with 150. And that 150 at the end of my products is equal to 16.7 grams plus, if we make this just like pure math, X. 150 grams equals 16.7 grams plus X grams. And X grams would be how much oxygen I have, right? So to solve for X, all I'm going to do is 150 grams, I'm going to subtract 16.7 grams from both sides to come up with X equals 133.3. Yes, 133.3. So taking 150 grams of water and decomposing it into 16.7 grams of hydrogen and 133.3 grams of oxygen. Law of mass conservation. Number 2. Any questions, first of all? Always, when I get to the end here, I may fail to say any questions, but please, if you have questions, raise your hand. If you have questions and you're not asking the questions, it's going to hurt yourself. I understand there may be some embarrassment or nervousness about not being able to, or not being willing to ask the question. I can't help you overcome that. That's part of what we talked about in my intro, right? You sit there and say, I don't get it, I have to have it for the exam. Mr. Baker, I still don't understand it. Now, I had one person show up for tutoring yesterday. So please, Mondays, that's when I'm doing my group tutoring. So I remind you of that as well. So, clear to erase? Lacking any input? Yes. Let's go on to number 2. Again, this type of question in number 1, number 2, this is just fundamental to chemistry. You're going to see this all the time. So be very comfortable with it now. Have it almost be second nature to you now. Where it says to burn a piece of wood. Remember that burning, combustion, is another type of reaction. Just like decomposition is a type of reaction, so too is combustion. Combustion is one of the 4 basic types of reactions we're going to talk about. So when I see to burn a piece of wood, I've got a chemical reaction. A chemical reaction that includes wood, in this case, as my fuel. And you're going to learn very quickly also that to have combustion, you also have to have oxygen. So fuel and oxygen and heat. Remember the fire triangle? Fuel, oxygen, heat for combustion. So if we have fuel, oxygen, and heat, which is energy, it's going to be added to these in order for this reaction to occur. Ash, carbon dioxide, and water. So we have ash, carbon dioxide, and water. Now we're going to go through and find out the mass of each one of them. If 3.8 kilograms of oxygen is used to burn a piece of wood, then what was the mass of the wood if the chemist collects 3.12 kilograms of water, 925 grams of ash, and 15.14 kilograms of carbon dioxide. Okay. I'm not going to do the whole problem. I think this is one of the ones we went over yesterday. But, again, fundamental principle is conservation of mass. That the mass on this side of the reaction arrow, all of this mass, must equal all of this mass. Okay. So to find out the missing piece here, what I would do was add up all the masses on the product side. So I get the sum of all of these. I would get a number here. And then I would subtract 3.8 kilograms from both sides, so that I'm left with the mass of the wood as the unknown variable on my left and the answer over on the right. So whatever the sum of these three is, minus the 3.8 kilograms that comes from the oxygen, the remainder must be the mass of the wood. issues. Yes, right.
Would you have to convert ash into kilograms before you add them all up?
You could convert ash to kilograms, or you can convert all of them to grams. Either way would work. So when I did this one the first time, I made that 0.925 kilograms, and I gave my answer in kilograms. Identify the following as metals or nonmetals. We're going to go where to do that. How do we figure out if something is metal or nonmetal? Well, there's two ways we can figure it out. One way is experimental, and that was part of the problem as well. One of the questions from the review questions. We can figure it out experimentally, or we can figure it out by using periodic table of elements. Let's talk about experimentally once, because there were some issues with the answers to that question. Remember, when we talk about how to figure out experimentally whether something or not is a metal, we talked about how you can take something and dissolve it in water, in distilled water. Remember, distilled water has all of the, as much as we can, has removed everything except H2O. So all the other ions that might be in the water are removed. And we've said before that pure H2O, which the closest we can get is distilled water, does not conduct electricity because it's not H2O that conducts. It's the ions that are in or dissolved in H2O that conduct. So if we have a substance and we dissolve it in water and it conducts electricity, then we say that it contains a metal. It's not all metal. It's a metal and a nonmetal, right? Because metals and metals don't combine. So if you have a substance that has a metal in it, when you dissolve it, it conducts. Some people wrote down it conducts because it has a metal in it. That's not true. It conducts because it has ions in it. And some of them are metals and some of them are nonmetals, but they're ions. Okay? But when we get that conduction, we know that it contained a metal. It contained a metal. On that note, someone wrote down as well, we know that something is a metal because it's solid. Okay? I've addressed that before too. That everything on the periodic table can be a solid, a liquid, or a gas, given the right temperature and pressure combination. Okay? So the fact that it's solid does not mean it's a metal. It's a metal because it has certain characteristics, primarily on how it deals with its outside electrons, its valence electrons. And we'll get into that in a lot more detail in a future module. But metal or nonmetal has nothing to do with whether it's solid or not. A chunk of coal is primarily carbon, and it's solid, and it's a nonmetal. Okay? It's the fact that it's a metal is other characteristics. Physically, we talked about luster, we talked about malleability, right? And then we talked about conductivity. Metals conduct, metals take a shine, and metals shape when you pound them. They don't shatter on the whole. That's general characteristics. The other way is just looking at the periodic table, looking at the stair-step or jagged line over here, and saying if it is to the right of that line, it's a non-metal. If it's to the left of that line, it is a metal. And we assume that it has the characteristics of a metal. And those which are along the jagged line, some folks said, well, the ones on the jagged line are metals, and some people said they're non-metals, and some people correctly answered they're metalloids. So, identify the following as a metal or a non-metal. It's not saying do this experimentally, it's saying there's a quick way. We're going to use the table over here since we're looking at elements, not compounds. We're not concerned with ionic or covalent compounds. Just is this or is this not a metal? The first one, Br. That probably is one of the ones you have to memorize, right? And what is that element then? What did you say? Well, that's fine. No, but I appreciate a wrong answer.
Beryllium.
No, beryllium is
Bromine.
bromine. Correct. Br is bromine. Bromine is over here. It's a column 7 element, which will mean a lot more to you again in the future. It's all the way over here. Bromine. It is strongly in the what camp? Strongly in the nonmetal side. Bromine does not want to give up any electrons. Bromine is fighting very, very hard to get electrons. It's a nonmetal. Okay. So bromine is a nonmetal based upon where it sits relative to the stair-step line. The second one, Sc. step back with you. Where is? Right over here, it's a column 3B. Pardon? Scanning. And it rests this side to the left side of the jagged line, so it has the attributes of a metal. I know P is not added. So you're correct, it's phosphorus. Where does phosphorus, is it a metal or non-metal? Non-metal, resting to the right of the jagged line, correct. Ra, way down here, column 2A at the bottom. What is it? Radium? Okay, I'll believe you. I don't know that off the top of my head. I doubt it's one of your memorization, but radium. And it is a metal or non-metal? It's a metal. Right. Like I said, it's going to be very obvious, hopefully very quick for you to recognize that these elements over here, especially column 1 and column 2, these are like the radical metals. These guys are trying to give away electrons. Please take my electrons. They're trying to give them away. And over here, columns 6 and 7, these guys are radically trying to get electrons. Does anybody play like the board game Pit anymore? Ever, you don't have to push any buttons or do anything like that with Pit. It's cards and a bell. No? Okay, never mind. It won't work then. But here's the whole idea. These guys are trying to give stuff away, and not everything wants to take. But over here, these guys are trying to take like crazy, but they're not going to give anything away. And so to form an ionic bond for an ionic compound, we get people to say, you know what, I want to give up 2. Hey, I want to take 2. Let's pair up. I'll take yours. And it's a giving away that creates the bonding. In covalence, I mentioned before, covalent compounds, nobody wants to give up because they're all nonmetals. They're all trying to hoard to themselves. They're all trying to keep it to themselves. They still want more, but as they look around themselves, they don't find anybody who wants to give up anything. They all want more. So rather than give it up, they share it. It's kind of like a couple of you guys going in and buying a car together. Bad idea, by the way. Don't do it. But if you did do it, if you were stupid enough to do that, nothing personal if somebody's actually done that. I'm not speaking to anybody secretly, okay? But if you did do that with someone, well then how do you figure out who gets the car when? Maybe you say, okay, we're going to alternate every night. Okay, then you got to manage that. That's a nightmare too. But managing it back and forth, back and forth. You say, you know what, I really want to have a car, but I can't afford to have a car on my own, so I'm going to go in with somebody else, and we're going to share the car. And it's going to alternate back and forth between each night. It's going to spend a night in somebody else's garage, back and forth, back and forth. That's kind of what happens between these nonmetals. They both want the electron. Neither one of them can get the electron on their own. They need somebody else, but the people they're pairing up with don't want to give it away. They want electrons too, so they say, you know what, we'll share one. You give me yours for one night, and then I'll give you mine for the next night. Go back and forth, back and forth. So actually, rather than having a full set, they are short sometimes and they're on sometimes, but they share back and forth. And I'm laying that basis when we actually get to that module, it'll make a lot more sense. Now we have done 4 and 5 already. Now we're getting short on time. But if we move, if we just think about the basic type of questions that we've had so far, and what you should expect from the actual math questions that'll be on the exam, hopefully by now you've picked up that there's a basic sequence. There's a basic sequence that calls for, okay, the first question is probably going to be something around this issue of conservation of mass, right? Conservation of mass questions are all about, hey, we've got this much on this side and this much on this side with an unknown on one side or the other. Solve for the unknown. It's going to be your conservation of mass problem. Then after that, there's going to be a balance. And again, I haven't even looked at the exam yet since last year, when I worked on it last year. But we're going to balance the reaction. And pretty soon I'm going to start using that terminology, the balanced reaction equation. When we balance the reaction, what we've done is we've worked the conservation of mass, and we found out that, hey, we might actually have excess somewhere. We might have an excess, we have something left over in the reaction. And how do you notice that something is extra in the reaction? Don't answer that. I got that question asked to me last night, so I'm cutting him out of the answer. What's that, right?
They don't equal the sign.
Well, they don't equal the same, but if I'm looking at a reaction, the first thing I'm going to do to see if there's any excess, and that's true, but usually they'll give it to me, and I'm going to look and see if I see the exact same thing on both sides of the reaction equation, on both sides of the arrow. You know, I've got some reactants here that produce products, and if I have something over here that's shown as a reactant, like hydrogen, and I look on this side, and I see hydrogen again, I see the exact same form. So in this case, hydrogen might be carbon dioxide is on both sides. If I see the exact same form on both sides, I have too much of it. Well, because what's that telling me is in the reaction, it wasn't all used up. I ran out of the other thing first. So I've got extra left over. I didn't need that extra in the first place, right? So what I'm going to do is, after I do the conservation of mass step, then I'm going to look at the next step and say, how much should I actually have mixed together to form the product? And only the product with no leftovers. And to solve that type of problem, we look at how much was left over and subtract it from how much we started with. So if I start with 100 grams of something and I end with 50 grams of it left over, I know that I only really needed 50 grams to start with. Or maybe a better way to put it, since it's not 50 and 50, if I have 100 and I end up with 25 left over, that tells me that I only needed 100 minus 25, or 75 to start with. I didn't need as much. So I'm going to subtract whatever I have left over from whatever I started with, that same atom or that same molecule. If it shows up again on both sides, I'm going to subtract the extra from my original to figure out how much I actually needed to have a perfect recipe. That's the phrase I've been using with you this module. The perfect recipe is a colloquialism that means the balanced reaction equation. Nothing left over other than what I'm trying to produce. Then, I've done the conservation of mass, I've done the balancing of the reaction. The next thing is going to be probably some multiple. I have done the balanced reaction, but now I need to produce an amount different than what the formula gives me. We're going to solve for the reaction multiple. This idea of the reaction multiple in review is just simply how many batches do I actually have to make to come up with the amount that I've been asked to produce. If I have this balanced reaction formula here and it produces a certain amount, I have a certain amount of one reactant and a certain amount of another reactant that produces a certain amount of product, and the question says, okay, but how much would I need if I wanted to make an amount other than the amount the recipe makes? And again, for Module 2, kind of an understanding, I have a recipe that makes 36 cupcakes, or I have a recipe that makes 12 cupcakes, a recipe that makes 12 cupcakes, and I'm trying to make 36 cupcakes, I need to make 3 batches. And so this reaction multiple, indicated by an X, is how many batches am I going to make? And when I figure out what that batch reaction multiple is going to be, please remember, this is the form. I know you're up to 1, but okay. The reaction multiple, what does it need to be? It needs to be how much do I need to have. So this would be right now we're working in terms of mass, let's say grams needed, grams asked for, to grams, I'll call this known. In other words, I have a recipe that will make a known amount. I haven't been asked to make the known amount. They haven't given me a question that's, okay, this formula will produce 25 grams. How much do you need to make 25 grams? Oh, there it is. It's right there in front of me. No, its question is going to be, you have a recipe that will make a certain amount. What's the recipe to make a different amount? So the different amount, what you're asked for, divided by how much your recipe will produce, creates a multiple. It tells you how many batches of your original recipe you need. And so once you have this reaction multiple, you go back to your balanced reaction equation. Not your initial one, your balanced one, and you multiply every mass on both the products and the reaction side by this multiple. Now your answer should, when you do that math, you should have, for example, A plus B produces so much C. When you go through and multiply with your reaction multiple, your formula then should look like A plus B produces so much C, and that so much C should equal what you've been asked to produce. That's your check. If you actually produce the amount that you've been asked to produce by doing the math, then you know that each reactant, each ingredient was multiplied the right way. Now, you should have picked up on last night's homework that there's a question there that doesn't give you the amount of your product, but it talks about one of the amounts of your reactants. And it works exactly the same way. If I know that I need a certain amount of reactant in my final, and I know how much I used in my initial, I still can do the same thing. Final divided by initial gives me a multiple. Multiply everything by the multiple. In other words, if my original recipe uses up 25 grams of something, but I actually end up using 75 grams of that in a final reaction, how much do I produce? I'm going to produce 3 times as much because I've used 3 times as much of that reactant, assuming that I've got plenty of the other reactant as well. So in that type of a case, you're going to be looking at the reaction equation and finding out what is your limiting reactant. In other words, what runs out. Because as long as you've got enough of what runs out, as long as you've got plenty of what doesn't run out to go with what does run out, the reaction will go all the way. Go all the way through and consume all of that reactant. So conservation of mass, balancing the reaction equation, then computing the reaction multiple. 3 basic types of problems. And those are both what 2, 4, and 5 are from this practice problem set. It's also what the mass, the bulk in the middle of your question set from last night. There are like 5 questions where hopefully you saw that they're virtually the same type of problem, just different numbers every time. And when you see that, part of you might say, oh man, I've already done a problem like this. Why are we doing another one? Remember, the extra practice problems are designed to address those issues which students where they typically make errors. So the reason why there's 5 that look exactly the same is because this is something that students often mess up. And they're giving you 5 more chances to practice it. Okay? That's why. So it's not an exercise in frustration. It's actually trying to give you what is a common error among students so that you can work on it. Number 6, what's the chemical formula for a molecule that is made up of 12 carbon? Let me make a little space here. Got 12 carbon, 24 hydrogen, 10 oxygen, and 2 sulfur. I sometimes put numbers like that in parentheses, and you know that I occasionally see right here where you might easily confuse that O and that 0. That's why I tend to do things like that, cross the O's, or cross the zeros so you can tell the difference between a 0 and an O. But this chemical formula that includes these 4 elements and these 4 quantities of each element. So what's the chemical formula? I'm going to take all of the counts and make them subscripts. All I'm simply going to do is go C12, H24, O10, S2. Because the subscript indicates the count of each element that it follows. The total number of atoms in that molecule, all we're going to do is count up the subscripts. And remember, when you don't see a subscript, what do you count? In this case, C3H6, C12O. The implied subscript for the O is a 1. So if you don't see it, it's a 1. If it's not a 1, they would have written it down. So 3 plus 6 is 9, plus 12 is 21, plus 1 is 22. And just count up the subscripts. Number 8, I believe we did this yesterday, but which of the following are covalent? You're going to assume a molecule is covalent unless you can find a metal, right? So determining covalent and ionic, you're searching for the metal. Another hint, if the molecule is written correctly, where is the metal going to be in the formula? In the very front. So look at the very first element. If it contains a metal, it's going to be listed as the first element in the formula for the molecule. So look at the very first one. First one, carbon. Is it a metal, non-metal? No, covalent. Second one, no, it's not a metal. Covalent. Third one, beryllium. Yes, it's a metal. It's ionic. Third one, lithium. Lithium is, yes, a metal. It's ionic. See See how quick that is? If you can look at the first thing, figure out if it's a metal or not metal. If it's a metal, the molecule is ionic. If it's not a metal, it's covalent. So naming those compounds in 8, C2H6, remember the paradigm. Take the subscript, change it to its prefix name if it's covalent, right? So in this case, C2 is going to be a di because it's a 2. So it's a dicarbon H6. So the prefix that communicates 6 is hexa. Put that in front, give it the I name. Dicarbon hexahydride.